to this Hertfordshire Geological Society virtual field trip to Little Heath. It's a site of special scientific interest because it shows evidence of a Pliocene shoreline high up on the Chilterns. I'm Clive Maton, and I'm going to take you through some of the history of the site with reference to 3 key geologists. Then we'll look at the exposure itself, as it was in 2012 when the last excavation took place, and look briefly at the results of that excavation, and finally a few words about geoconservation of the site. But first of all, let's look at where we are. Here's an outline map of the Chilterns from Reading up through to Luton, and the scarp face looks towards the northwest, whilst a whole set of chalk streams drain the Chilterns to the southeast. Little Heath, you can see here, is at about 170 metres above sea level on the dip slope of the Chilterns, sitting above the valley and the town of Berkhamsted. If we look at that area more closely, here's Berkhamsted with the River Bulbourne and the Grand Union Canal running through it, and up on the hill, the village of Potton End, with in its boundary the area known as Little Heath. And the part that we're particularly interested in is this area of woodland, owned and managed by the National Trust. And you will have, when you came here, you will have parked your car at the crossroads and walked down the road to meet me at the site. And as you walk down the road, this is what you're seeing. It's an area of regenerated woodland over the last 100 years. We know that during the First World War and before, this was true heathland. The owner at the time, Lord Brownlow, had a contract for the nearby town of Hemel Hempstead to deliver roadstone. And his people dug a number of pits that you can see one in front of us here, and you see them all over the woodland. They go down to about 3 meters in places, and others of them are just scrapes in the ground. And that shows that it wasn't a constant bed of pebbles that they were able to excavate. They must have been much more sporadic. So had they been a bed, we'd see much more of a quarry type site today. We're very fortunate that an amateur geologist was around during the First World War to do some recording of what he could see. And that's our first geologist, Charles Gilbert. He was actually the manager of the Cooper's chemical work, so an amateur geologist. Cooper's had been around for at least 50 years by this time, mostly manufacturing their patented sheep dip. This was a marvelous mix of sulfur and arsenic. So it must have been a delightful place to work. No doubt that might be why he spent a lot of time walking the hills around Berkhamsted. But he spent his time well, because in 1919, he got a paper published at the Geological Society on the occurrence of these deposits of sands and gravels up on the chalk at Little Heath. An excellent paper. His sedimentology description still stands the test of time today. Here's Charles Gilbert on site, looking at the sands and standing virtually on top of the gravels below. All this lovely exposure was all dug out by spade and shovel, so a pretty marvellous set of work by the workmen there. The picture itself is actually drawn from an excursion to Berkhamsted and Little Heath, also in 1919, by the GA. I rather wonder what participants there would have made of coming on a virtual field trip. We'll never know. Anyway, let's summarize Charles Gilbert's work. He didn't find any fossils, so he couldn't put a date using that method. His conclusion was that it was a beach or shallow marine environment, and probably of Pleistocene in age. Now, at the same time, or soon after, another geologist was working. And this is Robert Sherlock, a professional geologist working for the BGS. And in 1922, he produced his memoir for the Aylesbury sheet, sheet 238. And we can look at his sheet, or at least an extract from it, of just the Paleogene formations as they are in Hertfordshire. Indeed, we're borrowing a couple of corners from a couple of other sheets. And what you can see here in pink are the Reading and Up North Formation exposures, and in brown, the London clay down towards the southeast. And you can see that the Little Heath area is marked on the map, but clearly marked as Reading and Up North Formation. In terms of what it could possibly be, whether it's Pliocene or Reading, then we have to look at what tertiary formations are known to occur in the Hertfordshire area. Clearly, we've got Up North and Reading in the Paleogene and early Eocene, followed by the London clay. We see virtually no evidence of the bag shots in Hertfordshire itself, but then there's this long break of over 40 million years to red crag in the Pliocene. That is known in Harpenden in Hertfordshire, and we'll come on and talk about that a little bit later. So the conclusion which Sherlock came to, again, no fossils found. I don't think he actually did any work on the site. Rather, he was visiting the site that was already exposed, perhaps with Gilbert. And he came to the conclusion that really he thought it was a new facies of the Reading beds, and therefore Eocene in date. If we now skip forward in time significantly to our third key geologist, and that's John Catt. Dane, a professional geologist, particularly in soil science, who also did a lot of work on the Quaternary, both in the southeast of England and in Yorkshire. He was also emeritus professor at UCL and a pillar of the Hertfordshire Geological Society. Unfortunately, John passed away in December 2017, and he's sorely missed by his family, friends, and colleagues. Now, John clearly knew a lot about Little Heath, and also was interested in the results of, actually it's a book rather than a paper, produced by Wooldridge and Linton in 1955 on the structure, surface and drainage in southeast England, where they postulated that there was evidence of a paleocliff all the way along the southeast face of the Chilterns, and used evidence from lots of sites in the area, including Little Heath. There was a lot of discussion about whether the rights and wrongs of this theory in the 60s and 70s. And eventually in the middle 70s, John started work on revisiting Wooldridge and Linton with his then PhD student, Andy Moffat. They visited all the sites, and in particular, they came to Little Heath, and they dug a trench, quite a narrow trench, but down several meters, and then augured their way down to the chalk. They published 2 papers directly on Little Heath, and those are summarized very well in the 2010 Hertfordshire Geology and Landscape book, whose main editor was John, and that's still available. We had a reprint of it not so long ago, and so if you go to the HGS website, you can find a way of getting hold of a copy, because it really is an excellent book on the county geology. So what did they find and conclude with their excavation? They identified the Reading beds being about 1 meter thick on top of the chalk. But when they looked at the gravel, they decided that was not part of the Reading beds for 2 reasons. Firstly, the fact they found some Hertfordshire pudding stone pebbles. Now, you may well be aware that Hertfordshire pudding stones are small, rounded black pebbles in a siliceous matrix. Very strong, very tough deposits formed in very hot climates in rafts on top of the land at the time. Now the pebbles that are within the Hertfordshire pudding stone are redding bed pebbles. So by the time that that's been weathered and eroded and transported and broken down to small pebbles of Hertfordshire pudding stone, that's many millions of years, so would rather exclude the idea that it was Eocene of date. Secondly, they found some quartz or quartzite, a few pebbles and some granules, which are not found in the redding beds. They went on and looked at the heavy mineral analysis of the sands and gravel and determined that they were very typical of a shallow marine environment, also finding a glauconitic lens, which, whilst not indicative, whilst not evidence truly of shallow marine, is indicative of a shallow marine environment. And when they did the analysis across many sites, they found a link to red crag because of the similarity of these mineral assemblages to Berkhamsted in Hertfordshire, where some fossils of red crag were found in the 1930s. There was also links to Lane End near High Wycombe and the Hadley Formation in Surrey. As an aside, when they looked at all the other sites which Aldridge and Linton had visited, they determined that they were fluvial in character, and so not part of a, likely to be part of a paleo cliff. Indeed, that was part of their proof with that and some other evidence that basically said that Aldridge and Linton were incorrect in their postulation of that paleo cliff. So what did their conclusions for Little Heath come to? They didn't find any fossils, and they had a hypothesis that this really was probably Pleistocene in age. They also produced a map, which is in their book. It was they worked from an original by West in 1972. It's in the papers and in the book, should I say. And what you see here in brown are the exposures of red crag, and green the exposures of chalk. And the red crag is evident right down on the coast near Waltham-on-Naze and further around on the Essex coast, virtually at sea level. It rises in terms of the height of where it's found to about 80 meters on the Essex Hertfordshire border. Then the fossils found at Berkhamsted are about 125 meters. And their hypothesis was that Little Heath was part of that, as was Lane End and Headley Heath and the Headley Formation, which would give us a profile of the transgression of the red crag right across southeast England, and the chalk not having been raised until after 2 million years ago, in the last 2 million years, should I say. What it didn't do was give a definite date to Little Heath. But John didn't give up on that and created a new excavation in 2012. And the focus on this was to get hold of samples to use in cosmogenic nuclide burial dating. This is a technique that didn't come in till about the year 2000, and it was suggested to John by a colleague at UCL, Tim Atkinson, and they put together a paper or a request to get their samples tested at the National Environmental Research Council facility up in Scotland. Now, I'm not going to talk about the theory and practice behind cosmogenic nuclide burial dating. We'll treat that as a black box as far as this talk is concerned, but we will talk about some of the results. So that was the prime aim. Secondary aim was to create a greater exposure than we had that was present in 1978, so we could study more of the sedimentology, and finally to preserve that outcrop for further study and public display. It was sponsored by Natural England as a SSI site and by the National Trust as the landowners. Sorry, too far. I was fortunate enough to work on this excavation and subsequent work with John. And we were also very fortunate that we did not have to dig everything out by shovels and spades. We had big boys' toys to work with. And you can do a lot of work with one of these, and they work very fast to create back a clean exposure that we knew couldn't be contaminated. We could drop down all the way down to the chalk, and if we reverse the view, we can see here the base of that pit, and here's the little flecks of white indicating the top of the chalk. And you can see the first few beds above it, which indicate the redding beds. So if we look at this exposure, which we're going to now study in a bit more detail, it's about 10 meters across, and another key part of 3 or 4 meters coming out this way. And each of these steps is about 1 meter in depth, going all the way down, as I said, to the chalk. If I put some annotations on that, we can see that the chalk is at 9 meters below the surface, overlain by about 1/2 meter of redding beds. We didn't do any work on the redding beds on this occasion because they weren't the target for the project. That was this lower gravel and sands. Now, lower gravel is picked out very clearly, but a very distinct falling contact with the sands, which gives us about 4 to 7 meters depth of the lower gravel. The sands at their maximum are about 3 meters, but clearly that's not the maximum of the original deposit because they've been eroded away by the subsequent deposit of the upper gravel. What I'd now like to do is work through each of these 3 beds in turn. So starting with the lower gravel. Here's a section of it with what you can see is a lot of cobbles. So in about 60% of the deposit is well-rounded cobbles, mostly flint, but other things as well, with some larger cobbles that are quite well angular. The cobbles themselves range up to about 80 millimeters in size. They sit within a matrix that contains everything from clay particles through every type of sand, granules, and different sizes of pebbles. So a very mixed deposit, certainly not a well-sorted deposit, but it is certainly consistently supported, consistently sorted rather. The only area where it differs we found was one lens of pure sand, about 1 meter in extent and about 1/2 meter thick at maximum, which was further up the bed than this, but it was following this bedding that you could see here, which is a very fine, finely picked out. Not particularly clear and not particularly clear all the way through, but it is there as a sedimentary deposition bed. So what we've done is interpreted this gravel as a high energy, shallow marine environment. That's supported by the work of Moffat and Catt on the mineralogical analysis that they did. And so what we're seeing is that this is likely to be, if you looking for a modern analog, something like Orford Ness today. If we move on to the Little Heath Sands now, but first of all, let's look at the contact between this lower gravel and the sands. On the right-hand side, the dip is about 16 degrees, 15, 16 degrees, quite gentle, but then we come to the middle and you get this inflection point in the middle, where it drops down distinctly, a little flatter, and then drops down again out of shot of this particular photograph. Now, all the way up this area of contact, there is a thick clay deposit, about 4 centimeters thick. Whereas when you get to this part on the right-hand side, there's no clay at all. So this could well mean that on the left-hand side, we've got a channel. We've got 2 channels that we're seeing here with a channel lag deposit of clay. Whereas up here, no clay, straight onto the sand. And they're quite possibly, this might be a beach or certainly something that gets sub-aerial environment where this bed was deposited. One final piece is that there is an extra piece of the gravel. Here's in the enlargement down the bottom, if I can get the cursor to work. Here's the top of the gravel. We then get some depositions of the sand, and then another deposition of a few centimeters of gravel, which dies out towards the right. And this could well be interpreted as a storm deposit. So we've got the gravel, sand start being deposited, then a storm deposits some of the sand back on top of some of the gravel back on top of the sand before the sand continues to be deposited. So if we go now and look purely at the sand itself, it's brightly colored and there's lots of white lines. Now, the first thing we have to do is ignore virtually all the white lines, because these verticals are tree roots, and indeed most of these sloping lines are also very fine tree roots, which are of course following the weakness in the lines of the bedding. So ignore those and let's look in detail at the sand itself. So we'll look first at in this area. Here are these beautiful finely laminated sands. They are different grain sizes, but they have consistently have about a 25% clay content in them. Indeed, in some places, like here, the clay is deposited as a line of its own, without any sand in it. It's well laminated, and here we can see some evidence of cross lamination, and also in places there's evidence of ripple bedding on top. You'll also notice at the top here we've got a fault. It's only a very small normal fault of about 4 centimeters, but it's indicative of a settlement fault rather than something that occurred during the course of the bedding. Now, if we turn and look at 90 degrees to the main face, what we have in the bottom are sub-horizontal beds that you can see across here. And this indicates that the beds that we were seeing on the main face were dipping at 16 degrees, and that is a true dip. The next interesting thing is that it's deposited in couplets. So you get sand, clay, all the way up through this meter or so below the horizontal step. About 140, 150 pairs of beds through there. Very typical of a low energy environment where the sand is deposited, but the water doesn't come back in again. It's got time to settle and settle out all those very fine clay particles on top of the sand. However, above the horizontal step, we've got no clay-rich layers at all, just discontinuous lamination. So indicating a much higher environment, a higher energy environment that's been deposited here. Still the same mix of clay and sand, a little bit more coarse, but it's essentially higher energy, before returning at the very top to some laminated couplets again, so going back perhaps to a lower energy environment. So what we interpret this to be is a set of tidal sands, prograding from right to left across here with a consistent dip of about 16 degrees. We've got laminated rhythmic bedding at the base, which would form perhaps on a sandbar, and further up a much more discontinuous bedding, higher energy, and so indicative of tidal channels. So a modern analogue for this sort of environment might be a barrier island. Here's Scalt Head in Norfolk, with the North Sea out beyond it. And behind the barrier island, you get this tidal inlet, tidal channel, and sand being deposited on the edges here of the tidal channels, most of which gets flooded at high tide. So let's move on now to the upper gravel. And the first thing to note is that it's a picture showing Jonathan Hunn, who managed the excavation work for us on the day and did an excellent job. The contact with the sand is clearly very irregular, cutting down in places up here down to at least 3 meters and more. The gravel itself is well-rounded flint pebbles, often cracked, and they sit in a silty clay matrix. If we look more closely at them, the ones that aren't totally rounded but show signs, aren't totally spherical but show signs of they show signs of orientation, typically dipping down into these excavated parts between the pieces of sand. So the interpretation of this is a periglacial solifluction deposit, with the pebbles being transferred from upslope. Strong cryoturbation takes place. That's a churning by frost, freezing and thawing action during the periglacial times, which take the pebbles and they then sink down into the ground in their clay matrix. So here's back to our periglacial pebbles at the top above the sand. Here, just less than half a meter, which goes back to what we were saying about the original digging during the First World War, with highly variable thicknesses of pebbles. So if they started here, they would have given up very quickly. However, there's another feature showing the periglacial nature of this landscape, and that is in this corner of the bed. On the right-hand side, we see this area where the sand has cut down through the pebbles, probably finishing another half a meter or so below the step. So that cut down through with highly mixed sands shows that this is undoubtedly another periglacial feature, an ice wedge pseudomorph. So freezing and thawing, the ice comes in here, the ice melts, and sand falls in its place. So, in summarize, with the 2 key beds, we have a marine gravel, 4 to 7 meters in thickness, channels with a clay deposit, possible subaerial beach, and a storm deposit covering the start of the tidal sands. The tidal sands 3 meters maximum shown here, but eroded by the cryotubation of these periglacial pebbles. Tidal sands being low energy to begin with, indicating perhaps a sandbar, and high energy tidal sands further above. Now what we did, having described this, is let's look at what we did for the cosmogenic nuclei dating. We had to collect some samples. And the way to do this, we collected some blocks of sand that were sent off to Scotland, which was fairly easy to achieve. What was more difficult was to find these quartz and quartzite pebbles, which was what we were going to use in the samples from the marine gravel. And John and I were delivered a bucket, digger bucket full of marine gravel from each of the successive steps down till we got to the redding beds that we could sift through. And here's a picture of John and I spending one of the many happy hours searching for these quartz and quartzite granules. Now, the term hen's teeth comes to mind. They were almost impossible to find. And to give you an indication of that, out of each of those huge digger loads of gravel, we found maybe 100, 120 grams of these quartzite granules. But having said that, they were vital. They were bagged up and sent off to Scotland for analysis. So now I did say we would treat the cosmogenic nuclei dating as a black box. I might have well have said a blue and white box, because here's a picture of the equipment up there. The samples are pulverized and put in at this end. They're read using this accelerator mass spectrometer, and in effect, the results come out of this end. Unfortunately, what comes out of this end is not a date. It's a measurement of a number of isotopes of individual elements that have been found in the sample. So those results are then put into a true black box of a whole lot of mathematics based on information about the site itself and the isotopes and the age and how the isotopes degrade over time or through their half-lives. And then that result is put into work so that we can do some distribution analysis using a testing in models, and to give a result something like this. Now, to talk you through this graph, up here is probability. Along the bottom is age in million years, so that's 2 million, 4 million, 6 million, 8 million years old, etc. And all of these black dots are individual runs through a model. And as it quite clearly says here, these are provisional results that have been worked on. There's more work still to be done, but it's quite clear that from this, that the best fit of the distribution of possible ranges for Little Heath deposits is about 2.8 million years, with a range, 1 sigma range of 2.3 to 3.7 million years. Now, all this work was done in the black box by Angel Rodes from NERC, do a superb amount of work to deliver that. Tim Atkinson, who worked with John to come up with the original proposal, did a lot of work in association with Angel and the results from that. And the three of us, Tim, Angel, and myself, are currently in the process of writing a peer-reviewed paper where we can publish all the results on the sedimentology and the age of the deposit itself when everything is ready to deliver. If we draw, though, a conclusion of this 2012 excavation and look back at our map that we had before, we can truly say that Little Heath at 170 metres is truly part of the Red Crag surface. And because of its similarity in chemistry, Lane End and the Hadley Formation must be there too. So uplift of the chalk has clearly occurred in the last 2 million years, probably pivoting on a line somewhere just out into the North Sea off the coast of East Anglia. So to do our little conclusion box again, no fossils found, and this time we did do some more work on fossils with the kind help of Liam Gallagher. We took samples of the clay and some of the sand, and he analysed it in 3 ways, looking for microfossils, looking for nanofossils, and looking for palynology. And he didn't find anything at all through that analysis. So I think we can clearly say that there are no fossils on this site. They must all have been leached away. We interpret clearly as shallow marine, and with that date of 2.8 million years places it firmly in Pliocene, and clearly new facies, this time of the Red Crag Formation. Now this is a great success, and we'll be pleased to publish this once we say got the final data together. But the success is really one for John Catt, and to that end John will be named as first author on this paper in his honour and memory, and quite rightly too. So that's all I wanted to say about the deposit itself and the results. Let's finally look at a little bit of geoconservation on the site. Here it was in March 2012 when the digger left, filling in the hole for health and safety reasons down to the chalk, and leaving us with these lovely deposits of sand and gravels clearly on display. The National Trust soon after this put a badger-proof fence around the site, which you'll see on some other photographs, and a notice board was put up just out of shot of this to give everybody, the public and anybody, an idea of why this site was so important. Now, for the first few years, we didn't need to do very much to the site in terms of geoconservation. So much had been stripped off this that nothing really grew. We could come back and clean up the face when we had visitors coming along to look at the site, that we would talk them through. But essentially that was all that conservation took. However, by the time we got to the winter of 2016, 2017, the site looked a little bit different. Huge amount of growth. You can still make out the main sandy bed, but really in quite a bad way. So Hertfordshire Geological Society stepped in, and we formed a working party to come in February 17. We couldn't come any later because the National Trust didn't want us on site really towards the end of March, when the birds are starting to nest. We had to get permission from Natural England and the National Trust to come on site because again, it's still a triple SI. So we spent a good morning working on the site and clearing the weeds and cleaning up the faces. And you can see here we're about 7 or 8 of us very busy at work on doing just that. You'll also notice that we were carefully socially distancing. So even in 2017, we were conscious of coronavirus or something. Anyway, that's what it looks like. And so the net result was this. So all the weeds cleared, the bed nice and clean. You could clearly see now the badger-proof fence that the National Trust put in place. So a great job. And each year since 2017, a group of volunteers have come together each February to redo the work, because unfortunately the weeds keep growing back. And so it has to be done each year, regular as clockwork. And this is a picture is actually, as you see here, the result of the work in February 2020. Well, that concludes our virtual field trip to Little Heath. I hope you enjoyed it. Goodbye.